Most people picture large solar arrays as passive mirrors, simply sitting in a field soaking up the sun. But converting sunlight into electricity is a highly nonlinear process. To actually capture optimal power as the environment shifts, the system has to continuously and actively adjust itself. That responsibility falls to the system's brain, a controller known as maximum power point tracking, or MPPT. Its entire job is to scan the electrical output and locate the precise sweet spot where energy extraction peaks. We used to physically stand on rooftops, manually tweaking equipment to find that peak. Hardware alone is never enough. Algorithmic optimization has always been the missing half of the solar equation. This topographical map visualizes energy output. Under perfect sunlight, the power voltage curve is a smooth mountain with a single peak. But partial shading from clouds or trees physically fractures that green mathematical landscape into a jagged, uneven range of multiple smaller peaks and valleys. The standard algorithm, Perturb and Observe, navigates by taking blind steps up the incline. If power goes up, it steps again. But in shaded environments, this fails. It climbs the first small hill it hits and stops, falsely believing it reached the absolute summit. The true peak remains undiscovered in the distance. Relying on blind algorithms in chaotic real-world weather leaves a massive amount of harvestable energy trapped inside the system. To capture that lost power, controllers must stop merely feeling the ground beneath them and start actually learning the layout of the shifting landscape. This is where reinforcement learning steps in. Instead of following rigid instructions, intelligent agents interact directly with the environment, updating their behavior based on a constant system of rewards. Engineers tested 2 AI models against traditional methods: SARSA, a reliable intermediate algorithm, and DQN, an advanced deep neural network. DQN estimates complex state action values instantly. It sees multiple routes simultaneously without walking every path. By mapping the entire terrain, reinforcement learning locates the global maximum, the true summit, rather than settling for the nearest local hill. To quantify the difference, researchers ran PNO, SARSA, and DQN through 3 escalating environmental stress tests inside a MATLAB and Simulink simulation. Stage 1 tests perfect sunlight. DQN extracts 304.8 watts versus PNO's 295.6. Stage 2 introduces fluctuating conditions. PNO lags and drops wattage, while DQN stays highly efficient. In Stage 3's partial shading, PNO is trapped at 470 watts, SARSA hits 488 watts, and DQN achieves 495 watts. The simulation proves the math. Surviving and optimizing within real-world environmental chaos requires a system that actively learns. Extracting higher wattage is the direct result, but the true breakthrough is that these algorithms do it without requiring a precise, pre-programmed model of the solar array to function. The data offers 2 distinct upgrade paths. SARSA provides a reliable, lower complexity upgrade for standard systems, while DQN represents the absolute limit of energy extraction. Because they update themselves continuously, these autonomous models instantly adapt to shifting weather patterns or the slow degradation of aging hardware. Manufacturing more solar panels increases our theoretical capacity, but intelligent controllers dictate whether that physical hardware actually meets its maximum potential. Integrating reinforcement learning transforms reactive arrays into autonomous energy systems, guaranteeing maximum power extraction no matter what casts a shadow.